Recording. Okay, so let's begin. So can someone just confirm that they can see this?
Yes, we can see.
Okay, great. Okay, great. So welcome to the FTC Ink and Metal shadowing program. So in this program, you'll get a series of opportunities to shadow professionals in STEM as well as our team. So this is an introduction meeting. This is the first meeting, and it will simply get you this basic knowledge about the first organization and the STEM values, STEM concepts. And today we'll have a more mechanical topic focus. So this slide explains what FIRST is. It's an organization that was created by a pioneering man, pioneering engineer named Dean Kamen. And Dean Kamen worked with another MIT professor. MIT is one of the great universities here in the States. And he worked with this professor named Woody Flower to create for the inspiration and recognition of STEM talent organization. So that's what FIRST stands for. And now FIRST hosts multiple competitions, all for robotics, but for different groups of people. So for one, we have the FIRST Lego League. And so I'm sure a lot of you have played with Legos. It's the robotics version of Legos, and it's a competition for that. Then we have the FIRST Tech Challenge, which is a mid-tier competition, and that's what Ink and Metal, our team, participates in. And then we have the FIRST Robotics competition, which is the most industrial level competition. And to participate and do well and to win in that competition, you really need to adopt the professional level fabrication methods and design methods. And only then will your robot stand up to the rigor of that competition. So we participated in the FIRST Tech Challenge, which is an in-between level. Okay, so this is muted. Good. So I just explained this, but I'll go over that first bullet point, that first set of bullet points. So to go into the robotics field, if you do not know all of these skills to some extent, you will have a hard time. For one, of course, you need both the software and hardware understanding. There's a conception that a lot of times going into a robotics team, you need to focus on one thing. That's not really true. You can do your job the best if you understand all parts of the robot. Because, for example, if you're doing something in CAD, and I can show you an example of CAD later. CAD is simply computer-aided design, and it's where we design our robot virtually before we actually build it. And that's where we find and troubleshoot lots of our problems beforehand. So if you understand computer-aided design, then the mechanical team, which builds that design in real life, if you are also a mechanical member, you will design things in CAD that are easier to build. If you are not a mechanical member, you might design a piece or a mechanism that works very well in CAD, but to build in real life is very difficult. And that's why you need an understanding of all parts of robotics. I personally involve myself in both code, mechanical, CAD, all of these topics. So I feel that I've understood our robot pretty well. Okay, so to the right here is the robot we built last season. And this robot paired with our outreach won us pretty great award at the state level and advanced us to the world championship. So essentially the challenge for that season was shooting rings into a goal. So you can see we have the intake mechanism, the one that picks up the rings. Then we have a shooting mechanism. We have these two sticks on the side to make sure rings don't roll past us and that we can keep them in our vicinity. And then we have a nice LED strip as an indication for our drivers. Okay, so that's an example match. And the bottom picture is an image of our robot, another image of the robot. Okay, so this is a render. The picture you see on the screen is not actually, we did not take that with a camera. One guy on our team, he took the CAD model of our robot and put it into a rendering software that produces a really nice image, which looks very realistic, but it's not really taken in real life. And this is very nice for putting in your final portfolio or final notebook to show to judges during the competition. So our robot consists of both, of course, software and hardware, and the software is written using Roadrunner libraries. So Roadrunner libraries are libraries which we use to navigate around the field. So later in this presentation, you'll see that we have odometers on our robot, similar to the odometers in a car. And by taking readings from these odometers and compounding them together and performing calculations using the Roadrunner libraries, we can determine our location on the field and our angle relative to our initial angle. And so this is the way we can write autonomous paths, that is paths which don't use human input. The robot can itself know where it is and then act accordingly. So the Roadrunner libraries take care of navigation around the field, but then the mechanisms on the robot themselves need to be programmed. So for that, we use a set of other libraries that have been provided by the First Tech Challenge itself, by the first organization. And we also use some of our own code to program the servo motors and the other sensors and normal motors on this robot. And those purple cylinders that you see, those are motors. And there are a few servos visible if you can spot them in the render, but we'll look at it in a bit. Okay, and then we have the hardware. The servo sensors and motors themselves are hardware. And we also follow one set build system. So maybe from GoBuilda, we'll follow that build system because you'll notice that when we're building, it's pretty useful to have a set build method or a set build. What's a good word for it? A protocol. I'll find a better word in a bit. But the point is, if we have, for example, all of our holes spaced 8 millimeters apart and having a 4 millimeter diameter, each hole having a 4 millimeter diameter, then fitting things together becomes very simple. And the thing is, GoBuilda follows that standard. All of their holes are 4 millimeters in diameter and 8 millimeters 8 millimeters apart. And so even when we're designing custom parts, we follow that same protocol. For example, that grid plate you see, I'll just annotate. This here is the grid plate. And you can see we have a grid of holes on it. And those also follow GoBuilda standards, even though they were not produced by GoBuilda. So that's an example of sticking to a build system. Okay, so this robot here was not made on the first attempt. And almost never will you get anything on the first attempt. The first attempt will usually be a very horrible idea. But that's the reason we follow a design process. So we follow this design process in order to produce our robot over multiple iterations. This design process gives a structure to our development and allows us to create a great robot like this after we've gone through this process multiple times. So the design process is a 6-step procedure. First, we look at our problem and make sure we understand that perfectly well. If we don't understand the problem, we cannot possibly hope to get a robot that will address the initial problem. The robot might be great. It might function perfectly well or exceedingly well. But if it doesn't address the problem, there's no point to the robot. So that's the first step. we discuss the season's game. Each season in FTC, one company will release the challenge or the game. So in this case, the ultimate goal game consisted of intaking or picking up and then shooting the rings, the foam rings. And then we got an idea of the basic mechanisms we'd need to accomplish that. So maybe we'd have a set of grippy rollers, placed very close to the ground and rotating in the direction of our intaking or in the direction of our robot, so that rings will be picked up from the field and fly into the robot. Then we'd need a flywheel of some kind to shoot the rings. And then we need a carriage to store the rings while they're in the robot, because surely the rings cannot be shot immediately after they're picked up. You have to wait to shoot them. So this is just getting an idea of the problem at hand. Let me move to the next. Okay, so then we go to the generate concept stage. And this stage, if you do not accomplish this stage to the greatest level, you will have difficulties in your future steps, in your CAD and your building. You'll have problems. So this stage is the brainstorming stage. In our team, we ask every member to sketch an idea for all of the basic mechanism ideas. And then we come together a few days later and we decide upon the initial versions for each mechanism. So, if we had a new chassis to build, a chassis is just, the chassis is just the base of the robot, the part that moves. On top of the chassis, we place everything else, but the chassis is the bare bones moving mechanism, the one with the wheels. So if we had to build a new one of those, we'd ask every member to build, or to sketch an idea for that. So you can see one sketch shown at the top left here. And then we'd come together and decide what's the first version that we want to use. And a lot of times aspects from each idea will, be used. Maybe not one idea will be used entirely. Maybe we'll use multiple parts from each idea. Then you can see on the right and the bottom left and bottom right, we have more images of an outtaking or shooting mechanism. So, we have the rings come, and then we have the motor, the flywheel, the orange one. And when the rings come in contact with that orange wheel, which is spinning at 6,000 rotations per minute, the ring will be shot out extremely fast. And that's the method we used. Okay, then we go to the develop solution stage. And developing our solution, what we do in the develop solution stage is we take the first idea from the generating concept stage, and then we implement it in CAD software. So, for example, there are multiple CAD softwares available. Either you can use the Fusion 360 or the Inventor software or the SolidWorks software or Onshape. These are all options. We use at the moment, we use the Onshape, but we were using SolidWorks and Inventor for a long while. So you can use any of these softwares to CAD your robot. You CAD the parts, then create assemblies and test those parts in the assemblies, make sure everything works. Sorry, who annotated on my screen? Please don't annotate on the screen. Thank you. I'll just clear that. Okay, so that's essentially what we have to do. We have to take our designs and transfer them to an initial version of CAD. So then we build that solution. You can see that chassis at the bottom. That's the chassis of our robot. And then once we had that CAD, we went and built it. This is also called the construct and test stage. So we build that mechanism, we test it. In the bottom right is an initial version of the intaking, the ring picking up system. So this green row here was what we ended up using. This entire system here, I'll in fact annotate that. This entire system from here to here, this is our intaking mechanism. And that's the third iteration of that intaking mechanism. The first iteration was something as horrible looking as this. There's literal masking tape on the plexiglass. And, in general, the system was very unreliable. But it's a first iteration, you're building that first iteration. And then you evaluate it. So clearly, that won't work. And so you determine the problems with that design in person, when you're building in the garage. In fact, this is not even the first iteration. That was the second iteration. The first iteration was truly horrible. We had this zip tied row of compliant wheels, rubbery wheels, and it worked to some extent, but it was really horrible. So then we moved to this, thinking, let's get rid of the zip ties, maybe just use different sets of types of wheels, maybe use smaller, more grippy gecko wheels at the back, and then use fatter, less grippy ones at the front. That did not work too well. So then we noted those points in person. And then we go back to this develop the solution stage. That's the essence of this design process. We iterate back to the CAD stage. So then we implement those changes in our CAD. We make those changes, and then we go in person, build it again. Then we see, oh shoot, we have these problems. So then we'll go back to the develop solution stage. We'll CAD those corrections. And then we'll go in person and build that new mechanism, that new improved mechanism. And then we'll test it and we'll see, oh, this works perfectly great. And you could keep infinitely iterating like this, but at some point you'll see that the improvements are extremely minor, or you simply don't have time to keep iterating that many times. At which point you'd simply have to stop iterating. But in general, this is the procedure by which you go about it. And then we have our presenting the final solution step, where we show judges what we've done with our robot. So this is an example page from our design process, from our engineering portfolio. Last season, we only had to present an engineering portfolio to document all of the work of the season. So this is how we present our final work. So the point of this design process is we understand the problem, then we start brainstorming solutions, then we take one of those solutions which seems promising, and then we transfer it to CAD, then we build it, evaluate that built solution, go back and CAD it, build it, evaluate it, then go back and CAD, build, and evaluate. And we keep doing that until we have a satisfactory mechanism. And then we present it to our judges. Okay, so now you have an overview of the kinds of mechanisms on the robot, but we have to talk about the components that are used, the components that are used in the mechanisms. So, oh, sorry. Can Sacred Heart Convent School please mute? Okay, it's okay. I'll just mute that. Okay, great. All right, and also, as I said, please don't annotate on the screen. Okay, so this page is not really required. We can skip it. So first we have the intaking mechanism. This is an example from a challenge 3 seasons ago, or rather 2 seasons ago in FTC, where we had to pick up these Lego-like blocks and then stack them on top of each other. That was the challenge of the season. So to do it, so to do that, we had 2 green gecko wheels, and they would rotate opposite to each other. So if you have 2 wheels, I'll just annotate that on the screen. If you have 2 wheels like this, one is rotating in this direction, and one is rotating in this direction. If anything happens to enter right here, these wheels will both force that object further in this direction, because these wheels are very grippy, and if something passes in between them, they'll both pull the object inward. So that's the point of this intake. That's how it'll function. These 2 wheels will rotate in opposite directions and then pull the block inside the robot. So the advantages, these are examples of problems with that intake that you could diagnose in person. So if everything works perfectly fine, this is a pretty quick mechanism. From the moment the wheels touch the block to the moment they are in the robot, that does not take very long. The block can be taken very fast, very quickly. But the problem is, if these wheels are not don't have the exact same tension on them, one will push the block more than the other will. And as a result, the block will kind of move into the robot in like at an angle, instead of directly going in that direction, it might get pushed like this, or maybe like this. And at that point, it will not fall into the next mechanism, and then it might just interfere with the rest of the robot, and that's problematic. So that's one problem. Okay. And yeah, so as I said, it also didn't place the block well into the transfer, and there's some issues with that intake mechanism. Then we have the transfer mechanism. So our transfer mechanism would take the block that our intake had just passed into the robot and then orient it such that our stacking mechanism can easily access that block. So here we have two rods, which will flip 90 degrees and simply pass that that Lego block into the other mechanism. It's a very simple thing. It's just a rotating structure. If we have our piece initially like this, it'll simply rotate like this and eventually become like this. And then the block will be tossed like this. That's the entire essence of that structure. And then we have our outtake. This is a set of linear slides. Linear slides allow us to travel very far in one direction. So if we had a tall structure, we can surely have just, a very tall stick on a robot, or a very tall structure on a robot, on top of which we can place our mechanisms. But first of all, that's not allowed in FTC. You cannot have such a large robot. The entire robot must fit within an 18-inch cube. And second, that's just bad design. Because, when you have something so tall, as the robot's moving around, that tall thing will wobble a lot and also cause imbalance for the robot. And you should not be doing that. So these linear slides allow us to compress very far. And then when we pull on the strings, the linear slides will get extended. It's a nice mechanism, which you'll see in the next few slides. So let me find that slide. Interesting. I thought it was there. I don't think it is actually. Yeah, here it is. Here it is. Okay, so this is just a more in detail explanation. So the point of the linear slide is we have a string, and then we have a set of stages that are each connected to each other. And so when we pull the string, other strings also get pulled, and then all of the stages move up together simultaneously. So one method is simply having one string passing through all of the stages like this. These are pulleys, by the way. They just allow the string to rest on top of them. So you can have one string flowing through the entire mechanism, or you can have multiple strings, one attached to each stage. So somebody tell me quickly, with this continuous design, what will happen if we cut the string? What will happen to all of the stages if we cut the string at any one point? Somebody just unmute and say. Does anybody know what will happen if we cut the string at any one location? It's perfectly fine if you're wrong. I just wanted to hear someone.
Will collapse.
Exactly, it will collapse. All of these stages will just break. They'll all fall down. The reason being, they're all connected by the same string. If they're all connected by the same string, then one break will cause all of them to break. But in this case, you can see we have multiple strings. They have the same effect though. They're just connected with multiple strings. So then somebody else, tell me what will happen if we cut this string here. What will happen to the rest of the slides if we cut one string? Can somebody unmute and let me know what will happen if we cut the string? What will be the effect on the slides? Okay, it's fine. Yeah, just don't be afraid to unmute and let me know. But the thing that will happen here is only one of these stages will collapse. So here, if we cut this, everything would collapse. But here, if we cut this, only this stage will collapse because the rest of this the system is still supported by other strings. So that's the advantage of the cascade rigging. But let's go back to our correct slide. Okay, so then there are other mechanisms for that season. We had, for example, a hooking mechanism, which would lower over a block and then clamp that block. So this was a difficult mechanism to produce. So it required very many iterations through the design process. And that's how eventually this final mechanism worked well, even though it was difficult to produce. Then we have the electronics, the sensors. So for one, we had to be able to recognize that a stone was there, that a block or Lego brick was there. If we did, how can you possibly pick it up if you don't know it's there in the first place? So especially during the autonomous period where you don't have a human controlling the robot has to know on its own, oh, there's a block there. So for that, we used a color sensor because we know surely that these blocks here, as you can see, the ones that are stacked, these blocks are yellow. And there's really nothing else on the field that's yellow. So we would go over to this general location where the blocks are, and then we'd use a color sensor to determine that a block was in front of us. And when we knew the block was in front of us, then we'd pick it up. So for that, we used a color sensor. Okay, and then we also had a servo mechanism. These servos are simply more precise motors. Motors are used to allow lots of force and torque and speed, but they're not really controllable too much. A servo offers less torque and speed, but you can control them very precisely. And that's why we use them in less intensive applications where we need precision and not speed. Okay, this page is just kind of a review. We already know this. Okay, so then we go into gears. Gears allow rotational motion. So these different types of gears allow us to transfer rotational motion in multiple ways. So the spur gear, this gear at the top left, this is the one we see very commonly. There's really nothing special about it. We simply have gears that mesh, and when they mesh, they transfer the rotation to each other. So if you have two gears, sorry about that. If we have two gears like this and they're touching each other, if one is rotating like this, the other will rotate like this. So after that, we have the helical gear. The helical gear has slanted teeth. It's very similar to the spur gear, but has slanted teeth. And does anybody here, can you guess what's the effect of the slanted teeth? It's not too obvious at the beginning itself, but if you can think about it, would anybody know what's that benefit of the slanted teeth? I'll give you around like 15 seconds to think. What's the effect of the slanted teeth?
Could you please repeat the question, what you asked?
Yeah, so I asked, we have the spur gear with straight teeth. You can see that these teeth here, they're straight. But here you can see that they're slanted like this. They're not straight. A straight tooth would be like this, but this is slanted in this direction. So I'm just asking, what's the reason that what benefit do these slanted teeth provide in the helical gear?
Less jamming.
That could be one. It could offer less jamming, but there's one more general stability centered benefit that these slanted teeth provide. Okay, so I'll go ahead. Go ahead, Said. Okay, Mirza, did you have an idea?
Friction for smoother gear operation.
Smoother gear operation and less friction. Okay, so both of those might be true. I'm not entirely sure myself, but what I do know for sure is that these gears allow us to keep them together without forcing them to be together. And the explanation for that is a bit complicated at the moment. I can explain it later, but the point here is when you have two helical gears that are meshed together, they cannot afford to move apart from each other. They will stay together. They might move
It
this
will
way. Go ahead.
it will reduce your shock loads and causing less noise and vibration.
Okay, yeah, that's true. But the point I was making here, the advantage of the helical gears is that they will not move back and forth. They will stay meshed together. So that's the reason that they offer an advantage. Then we have the double helical gear. It's quite similar. Um, we just have two rows of teeth instead of one row. It's it's like we're taking this helical gear here and then mirroring it. So we have another set of teeth. Um, and so it just offers more surface area, um, and therefore greater contact and stability. Then we have the spiral bevel gear. The spiral bevel gear is an interesting point because if we have 1 degree of rotation in this direction, we can transfer that to a perpendicular degree of rotation. So here, we have this axis of rotation, and that's being compounded, or rather, it's being transferred to this axis of rotation. And so it's valuable when your motor cannot necessarily be aligned with the wheel. Sometimes that's a design restriction. Your motor will have to be flat, but your wheel will have to rotate in another direction. So in that case, you can use these kind of gears to allow that. And the miter gear and straight bevel gear are very similar versions of that, but they just offer different amounts of torque and stability. Then the internal gear. The internal gear is very commonly used in gearboxes. In fact, I'll just escape this quickly and go over to show you a planetary gearbox. So here's an example of a planetary gearbox. And so you can see this is a set of multiple internal gears. And through this set of internal gears, you can achieve extreme gear ratios. And I'll tell you what gear ratios are. But essentially, you can change your torque and speed extremely fast by simply using a set of internal gears, and this internal gear contains everything within itself. So you have a lot of nice gears going on within a small space. That's why they're desirable. And then we have the worm gear. This offers extreme amounts of torque and very little speed. And then we have the rack and pinion, which allows us to travel back and forth along a set of racks. And I'll actually show you how that works in a little bit. So actually, in fact, it might be nice to show you that now itself. Let me just go to our ink and metal YouTube channel, and I'll give you a look at the trash sorter demonstration. So this is a project we've been pursuing recently, and you can see at the back here, we have a rack. It's a bit difficult to see from here, but we have a rack and pinion system. If I zoom in right here, you can see the ridges of that rack. And then behind this mechanism, there's a pinion. It's a small gear. And when that pinion rotates, it pushes against those teeth and moves in this direction. So that's, how we use it. So here's a practice problem about mechanical advantages and gear ratios. So when we use different numbers of teeth and different gears of different diameters, we get trade-offs. So we can either in this entire system have lots of torque and no speed, or very low speed, or we can have lots of speed and very little torque. The value that you want to optimize is specific to your system or specific to the mechanism you're building. If you had a situation where you need lots of force, but your speed is not really a priority, you'd use a high torque and low speed motor. If you wanted not really too much torque, but you need lots of speed, you'd use a lower mechanical advantage to achieve that. So the formula here is the torque that we input to the torque that we output. The ratio of those two torques is equal to the number of teeth of the input gear to the number of teeth of the output gear. So somebody do this problem quickly, if you were able to solve it, and let me know what the value we need to find is. So our input gear, this is our input gear, the small one, it has 8 teeth, and our input torque is 10 Newton meters. And then this second gear has 13 teeth. The output gear has 13 teeth, and we want to find what's the output torque. So let me know quickly, do the calculation, and let me know by unmuting what your answer is. So we're just simply finding the output torque using that formula. And when you're done, just unmute.
17.
Okay, let's see if that's correct. So sorry about that. Okay. So we have 8 teeth, or rather not 8 teeth, 10 Newton meters to 8 teeth equals our output torque to our 13 teeth. Okay, and so we simply solve by doing this times 13 teeth and then canceling these, and then we simply solve it. So if we just load up our calculator, we do 130 by 8, and that is about 16. So you're quite close. It's more around 16.25. So our output torque would be 16.25 Newton meters. Okay, so these spur gears I already explained. They're not needed to be explained anymore. Rack and pinion. Oh, I wanted to give you a nice example. I showed you one example of the rack and pinion in our trash sorter, but this is like the other rack and pinion example in the car. When you turn the steering wheel, these wheels will be turned in different directions. So yeah. And then we can go past all this. I explained all this. I explained linear slides as well. Essentially, we just have a group of moving stages that are all propelled by a string. This linear actuator is simply an application of gears and extreme torque, but very little speed. That's the application of this system. When we want to, like, for example, lift our entire robot, that requires a lot of force, a lot of torque, but we don't really need to do that very fast because we don't have to lift a large distance. We can afford to lift very slowly. So in that case, we'd prioritize torque. And so we'd use a worm gear system because the worm gear offers lots of torque. Okay, sensors. So I talked about this color sensor already. What it does is simply emit white light onto an object. And then, of course, the object will only reflect one color. It'll absorb all the other colors and emit one color, reflect one color back. And that one color that's reflected back is then recorded by the color sensor and then displayed. Then we have the tactile switch sensor. Essentially, we click the button and we have two possible inputs. Of course, not pressed or pressed. It's not very complicated, and the sensor understands that. Then we have our distance sensor. Either we can emit sound or light at an object and record the amount of time that object took to get to the object and then get reflected back to us. And because we know the speed of sound and speed of light, and we also record ourselves the time that was taken for that object to for that light or sound to hit the object and come back, we can simply plug that into our D equals VR equation and determine the distance to that object. And when we use 2 or 4 distance sensors together, we can use the walls of the field we can use the walls of the field as reference points and then find our distance relative to those walls. But then a problem is, what happens if another robot comes between your distance sensor and the field? Your robot will think it's closer to the field than it really is because something got in the way. So in that case, you'll have incorrect localization. So that's why we generally don't use distance sensors when we're navigating. Then we have this nice camera. This camera integrates lots of different sensors. First, we have the camera itself, of course. Then we have our distance sensor, which can, creates a map of its surroundings, as you see in the bottom. Then we have a LiDAR sensor in this. That's basically the distance sensor, which uses light. So it's used by a lot of teams for navigation, but it's very hard to implement because it's so complex. Then we have an inertial measurement unit. This inertial measurement unit uses a very tiny gyroscope to determine our current heading, our current angle relative to our previous angle or to our initial angle. And this is how we angle ourselves correctly to shoot rings or, just drop an object in a target location. Okay, so these are different localization methods. As I was saying, we have the odometer. This odometer consists of 3 parts. Let me just show you quickly the 3 parts. The odometer has these few parts here. We have an electronics board and photo detector, the code disk, the light source, and the housing. And every time the motor shaft turns, one of these black rings will pass over the light source. And those black rings will dim the light source. And this photo detector realizes that the light has been dimmed and knows that 1 tick has passed over the light source. So that means that the motor has rotated by some amount. Each tick signifies some amount of rotation. And then our photo detector knows we've traveled that much and then transfers that to the electronics board to transmit that reading. And then when we've traveled, some number of ticks, when the photo detector has detected some number of ticks, it realizes we've traveled X distance or some amount of distance. And so that's the essence of an odometer. And when we use them in conjunction with each other, they allow us to determine our position on the field. Okay, and I already explained this distance sensor. Okay, so that is about it for this presentation. So my question to you guys is, did you have any questions about these topics? We have about 10 minutes left, or about 5 minutes left, actually. So we can go over any questions that you all are having. Let's go to the chat. Okay. So did anyone have questions about any of these topics? Anything about, the first competition, what we'll be doing in this program, generating concepts, the design process. If you guys don't have questions, that's perfectly fine as well.
Yeah, feel free to ask if you have any questions. And if you don't feel like speaking up, you can also just put it in the chat.
Okay, in that case, I think session can be ended here. So thank you guys very much for coming. It was very awesome teaching you guys. You had some great inputs. Okay, so that's about it. Adios.